Alright, so we're going to get started today. Welcome back. We're in week 7, 8. We were debating before class, we're not sure. Whatever, doesn't matter. Almost through. Yeah, so as always, you have a homework due today and another one going out. This one is shorter, but it involves some coding in MATLAB. So if you're not used to MATLAB, you should get used to it now, because you're going to use it. And thankfully the coding isn't anything too complicated. It's just addition, subtraction, for loops, and matrix multiplies, which, as we know, comprises the entire conjugate gradient algorithm. Because I was looking at other people's problem sets on conjugate gradients, and sort of I feel like the problems kind of fall into two categories. It's either like abundantly obvious things that you check just using algebra, or like ridiculously hard statements about Karloff spaces, and I don't feel like it's fair to ask you guys that. So instead, I'm going to have you actually implement CG and see what it does. And so I figure, so that you have some idea of what I was looking for, I'll show you my implementation of the homework to prove that a solution exists. And from there, it'll be your job this week to reconstruct it. Right, so the problem that I'm having you solve is a problem in graph layout. So the idea here is that let's say that I have an artist, right? Or let's say that I have a graph, for one thing. Do we all know what a graph is? It's a collection of vertices and edges. Yeah? I think they cover this in 102. If not, it's pretty simple. Right, so I have this graph, which is a topological object, meaning that it has vertices, it has connectivity, but if I want to actually draw the graph on the board, I have to decide where to put the vertices. You know? And so a good criterion is that I want to put the vertices in such a way that things that are connected by edges are close to each other, because that way sort of you're going to minimize the amount of clutter in your graph. Yeah? So the problem that you'll solve on your homework is that, let's say that I specify some vertex positions, right? I'm an artist and I want to lay out my graph. And your job is going to be to fill in the remaining ones. The way that we're going to do it is we have this energy that I call the Dirichlet energy of graph. And basically, it's measuring the length squared of each of these edges and just summing them up. And you want to minimize that, right? Because that somehow keeps the edges short and your graph very clean. In fact, this is related to some very classical theory, but we're not going to worry about that. So anyway, so your job on this homework is to figure out the linear system of equations that gives you that graph layout, which you've basically done in previous homeworks, but you're going to do it again. And then you're going to code up that matrix and solve it using conjugate gradients and gradient descent. And what's the kind of neat thing is that CG, by the way, don't look too closely at my code because that's the answer. But the idea is, in fact, actually, I think you do, but I don't care. It's mostly for your edification. The conjugate gradients and gradient descent are these different tools that just iteratively are updating estimates of your solution. And in this particular case, usually has a very concrete meaning, right? It's just a set of positions of vertices. So you can actually see your vertices move around as CG and gradient descent run. So I thought I'd show you what that looks like so that you can see that it's not totally wild and crazy and have some reference to your solution. So first of all, I actually give you a little piece of code, and this is in your starter code. Here, that just uses MATLAB's linear solver, which is going to be way faster than the code that you write, but that's okay. And this way you can check your answer independent. So you can check that your AX equals B is right before you start checking that your conjugate gradients is right. Yeah. And so in particular, if you run this, I give you a graph of a circle, and our artist has fixed all the positions of the vertices around the outside part of the circle, and your job is to fill in the positions of all the rest of the vertices, yeah, using this elastic energy. And so this is the output that you expect. And the kind of neat thing is, if you run gradient descent, you can see the vertices move around kind of like the edges are springs, because that's what gradient descent's doing, right? It's trying to decrease your energy. The other thing you should notice from this example, this was actually last night at like 3 a.m. I was trying to tune this example to make sure that you really see what's broken here. You can see that it takes forever to converge. And so conjugate gradients is like slowly relaxing these springs, but they're all kind of fighting against each other, and so the convergence is very slow here. It's not so good. And eventually it does kind of work itself out. It's kind of fun. It's like oddly mesmerizing. Right. So that's gradient descent, and then if we run conjugate gradients, you'll see, and don't look at my code, that it kind of snaps right to the right answer very quickly, which is surprising. So anyway, so that's your job on the homework, is to implement these two solution techniques, and then a little bit of code to visualize what's going on each iteration, and play with it a little bit. And then your extra credit, unsurprisingly, is to come up with a preconditioner and see if that helps your convergence at all. And this is a Laplacian system, and it's a very well-studied thing. If you go online, you'll find tons of preconditioners you can play with, or you can use one of the ones we covered in class. Yeah. In fact, MATLAB has a built-in incomplete Cholesky preconditioner, and you are welcome to just call their function. I don't even care. It's all good. Cool. So any questions about the homework? You have one due today. This one's going out. In fact, it went out this morning. There are also 2 written problems, but they're relatively short.
Is there any better MATLAB?
Well, if you want to take my code and put it somewhere else, I suppose I don't really care. Yeah. It has to be done in a way that demonstrates to me that you understand the course material. Yeah. Okay. Any other questions? Martina?
So you just email the code to you?
Yeah, so just submit it, just like the people that have been submitting their online, there's, the problem that's online, just send like it's just one file. Yeah. Anything else? Well, that's a good place. And if you've never used MATLAB, get started a little early. It is built in on all the CS department machines, and it's really easy. Yeah, so I'm not too worried about how you guys are, at least the parts that we'll be using. And I provide you with all the code for drawing the graphs and that kind of stuff. Cool. So it's actually kind of fun. You get to see these guys in action. But for today, we're going to do something completely different. So, right. And sorry, I owe you a proof from last class, and I forgot about this until I was walking the room. So I will do that on Monday. I promise you the resolution is not very complicated. Anyway, so thankfully, I would say that the conjugate gradients algorithm is sort of the height of notational hairiness in CS205. And from here on out, things are going to get sort of much more intuitive, easier to draw, and easier to think about. Of course, I keep using this word easy, and everybody rolls their eyes at this point. So you are welcome to make your own judgment in that regard. But I do find that this material is sort of more geometric, and certainly as a geometry researcher, for me, this is much easier to think about. So, right, so today we're going to talk about interpolation. So far in CS205A, I'd say we've really talked about tools for analyzing functions. Right? Like for example, in the last couple of weeks, we've developed algorithms that can find the minimum of a function, that can find the roots of a function, that solve particular linear problems, and so on, right? But there's a fundamental assumption in all of these algorithms, which is that, for one thing, I have a function f of x, and that given enough time at least, I can query f of x for any x and get an f value back out. Right? Sort of the fundamental assumption. But I would say that that's not always the case. Right, and in fact, a lot of times, really the unknown is the function itself, and we won't get too philosophical about this. In fact, there's an entire area of calculus that basically says, like, if I'd like to minimize energies that are functions of functions, there are ways to deal with this, and it's super fun, but you can take my 468 and we'll learn about that. But in the meantime, sometimes we just have information, but it's only sparse, and we have to fill in what a function is everywhere in between. This is a totally reasonable thing. For example, in image processing, let's say that I take a digital photo, right? So I think even if you've never actually written image processing code, it's pretty reasonable to guess how it goes, right? Where you have a photograph, and basically he's represented as a grid of pixels, right? So you can think of this as like a little lattice, right? You've got little pixel values sitting on each of these vertices here, right? But now let's say that I want to rotate my photo by any angle that's not a multiple of 90 degrees. Yeah? Well, how am I going to do that? Well, effectively, you can think of my output photo. I should probably use another color. It says you can draw a second grid on top of the first one that's rotated by the angle that you want, right? So maybe now I'd like to rotate my photo like that. Yeah? So I draw some new grid, right? And my output is going to be the color values at the lattice points on this new grid, right? Because we've rotated. But there's a problem, yeah? What's the problem? Is that the lattice points on this new grid don't align with the green ones, right? So we have to somehow fill in the color information in between all of these green points in a reasonable way in order to rotate photographs. And in fact, you can come up with really evil examples where you have this reasonable algorithm for rotating an image 1 degree, and if you run it like 360 times, rather than just getting the same image back out, you get just total gobbledygook. So in fact, there's very, very rigorous sort of sampling theory and very rigorous theory of interpolation that's hiding underneath this. In one lecture, we will hit approximately none of that, but if you are interested, you should come talk to me, because this is my kind of bread and butter. Another example, by the way, other than just image processing, is in machine learning, right? So for instance, maybe, I don't know, maybe I'm at a hospital and I can administer different dosages of medicine to my subject, right? And we kind of assume that that's a continuous function, right? The more insulin I give you, your blood sugar kind of continuously changes as a function of that. But obviously I can't try every possible, value of input thing, right? I have discrete samples. And I'd like to be able to predict the behavior of this function in between. Okay? Totally reasonable problem, I'd say. Doesn't need a whole lot of motivation. Cool. So what is our input and our output? Well, basically we're going to get a bunch of pairs x comma y, right? And here we're going to say that the x is in some Rn, right? And that each x is going to map to some output y. And for today, we're going to assume that we know the value y exactly, right? So our interpolated function should respect the values that we know and simply fill in something reasonable and continuous in between. If that doesn't hold exactly, then this is an instance of a slightly different problem called regression, right? Where maybe your y values are somewhat noisy, so it is not desirable to respect those completely, but rather you would prefer to have a smooth function, right? And if you're interested in regression, I believe CS229 covers some basic material on that, and then you can go to the stats department for more. But this class, we only get one lecture, so. All right. So as always, as with root finding, as with minimization, as with just about anything we've done in 205, we're going to say, okay, our initial problem we're going to try and solve is simply finding a function from the real numbers to real numbers, rather than a function from Rn to the real numbers. Right? And then we're going to take these basic strategies that we develop and we're going to extend them to the more general case. Yeah? It's a good pattern in numerical computing. All right. So in particular, what is our input now? Well, we're going to say we get k pairs that are just x comma y. Right? These are just two scalars. And now we're going to say somebody gives me some x that isn't one of the xi's, and my question is, what should the y value be? Yeah? Okay. So we've actually already covered lots of different methods for this, but the underlying problem here is that the set of all functions that takes in a real number and gives out a real number is a ginormous set, right? It's uncountable, it is like uncountably uncountable, it is just humongous, right? And you can't expect to work in this kind of a set. And in fact, even theoretically, right, when we talk about problems of interpolation, we usually restrict ourselves to particular classes of functions that are better behaved, because these include fractals, they include discontinuous things, they include God knows what, even unmeasurable, big, unhappy functions, and we don't want to deal with that. So in fact, in CS205, a common strategy, and in fact, not just in CS205, but in life, is to restrict our search for this interpolating function f to a set of basis functions. Right? So remember in linear algebra, right, we have this kind of generic problem where I have some vector and I'd like to express him as a linear combination of some other vectors, right? We call those the basis, and then we have this new guy and we're going to solve a linear system. Well here, we could try and come up with a basis for function space. Right? Again, this is another tip of a humongous iceberg, like what is a basis for function space? That's not something we worry about. But right, we can write down some basis for the functions we care about at least, and that allows me enough fuzziness to make this lecture okay. And based on that, we can say, okay, well, I'd like to come up with a reasonable approximation or interpolation based on the data I know. Yeah? And somehow by limiting the number of basis functions, our search problem becomes more reasonable, right? The set of functions is just really big. And it also kind of regularizes the smoothness and behavior of the functions that we're dealing with. Yeah, I think it's a reasonable approach. So what's going to happen is that we're going to think of our function f of x as just a sum of a bunch of ai times these different phi I basis functions, and our unknown here, lucky enough, is now a vector. Yeah? In fact, it's a vector of just the coefficients in front of these basis functions, right? So I just took a problem that could potentially look like God knows what measure theoretic nightmare and turn it back into linear algebra, which is good. We like linear algebra. Okay, yeah, this is CS205. If you like the other stuff, you should take Math 205, incidentally. Okay, so one basis that shows up both theoretically and in practice a lot is the basis of monomial functions, right? And that is nothing more than the basis of functions that look like 1, x squared, x cubed, x whatever comes after cubed, fourth, and so on. And this is a basis for the set of polynomials, right? So sort of the most basic problem you could think of is find the degree 5 polynomial fitting through these 5 points. Right? And if you recall, back from week 2, we actually saw this as sort of a side note based on a more general observation we made about least squares, but maybe I'll remind you. So in this case, right, our function takes this form f of x equals a0 plus a1x and so on. Yeah? So how many x's do I need to find f? In the form that I have here. So I have from 0 to k minus 1. K minus 1 unknowns, so how many x's would you make? K minus 1, yeah. No, k, because it starts with 0 and goes to k minus 1. Sorry. So, right, so in particular, we have a bunch of x, y pairs, and we get a bunch of expressions that look like this. So we're going to have, for example, y, I don't know, how much is yi equals a0 plus a1 xi plus a2 xi squared plus, and so on, right? A k minus 1 xi to the k minus 1. Yeah? Now what are our unknowns here? It's the a's. Right? This always trips people up. The unknowns here are the a's. These guys. Right? So in fact, this is a linear equation in the things that you don't know. Right? These numbers, yeah, they have exponents and stuff, but they're just numbers. Right? They're input values because somebody has given us these x and y pairs. Yeah? So in particular, what I can do, and this holds for k different examples, right, for all these different objects, and I can smash this into one big linear system of equations, right? And yeah, so here we're going to have, this is not a good marker, we'll switch in a second. Equals some stuff, okay? And what is it? Well, we know we have the yi's over here, right? That's y1 to yk. Yeah? And then what is the matrix of this linear system of equations? Well, you can kind of read it off, right? It's 1, x1 squared, and so on. Yeah? So 1, x1 squared, all the way to x1 to the k minus 1. And then 1, x2 squared, to x2 to the k minus 1, and so on. Yeah? So all I did was just encode a bunch of relationships of this form in a linear system of equations for the unknowns, which are the a's. Yeah? Anybody remember what this system of equations is called? Yes, it is the Vandermonde system. Right? And so this matrix is very easy to construct, and in fact, there are special algorithms for inverting this matrix, but this is far outside of the scope of this class and somewhat useless. So, but theoretically kind of fun to play. Yeah? So anyway, we now have a way to fit polynomials to a set of data points, right? And in fact, this respects our data points exactly, right? Because we started by a bunch of equality constraints, right? So this is a method for interpolation and not for regression. Well, I guess it's sort of for regression too, but not very much. Cool? So the question is, can we do better, right? How long will it take to find my f of x? Well, we know this is just some k by k system of equations, right? So it's going to take k cubed time to invert this thing using Gaussian elimination. This matrix is certainly not symmetric and probably not positive definite, so I don't think that a lot of the machinery we developed last week applies. Yeah? So you're back to some of the old tools we have. By the way, chances are we're not going to solve this for humongous k because all kinds of strange things can happen. But we'll come back to that in a moment. But anyway, one way to motivate why this strategy, this set of basis functions for the polynomials is a little weird, is to actually just plot the darn things. Yeah. So let's take a look. So here are my axes. Yeah. So here's x, and here's we can call the nth polynomial piece of n of x. Yeah. And here's 1. And here's another 1. Okay. So what happens? As n increases, well, the first polynomial, is just a line. The second one is a parabola. The third one is kind of a more flat parabola. Fourth one is an even more flat parabola. Fifth one is an even more flat parabola. Yeah? I shouldn't be using the word parabola anymore, right? But whatever. But all these functions kind of look the same. Yeah? And as you know, that is a really bad property to have when you're trying to project things onto the span of a set of vectors, right? Remember why, like, for example, when we were talking about Gram-Schmidt, right? And Gram-Schmidt orthogonalization, in fact, you drew a picture of this on your midterm, I hope. Or you drew one after your midterm and felt that you didn't draw it on your midterm. Where if you have a bunch of vectors that are very close to being parallel, right? And then you're trying to project onto the span of these things, bad things happen because it's unclear which vector you should follow. Yeah? And in fact, the polynomials, as n gets really big, end up looking very, very similar to one another. At the end of class, we'll actually come up with a formal way to express that relationship if we have time. So anyway, these are by no means the only basis for the set of polynomials, and in fact, our friend Lagrange introduced a much better basis that's very much tuned to the problem at hand. So the Lagrange basis is exactly the one that I drew on the board here. Has everybody seen this pi before? This pi means product. You know, the same way as sigma means sum, pi means product. This is a product of a bunch of terms. So first of all, does this thing look like a polynomial? No, right? We're kind of used to looking at polynomials as like x cubed plus 3x squared plus whatever. Yeah. But do you agree with me that the product of two polynomials is also a polynomial? I think so, right? Like for example, x cubed times x squared is x to the fifth. That's still a polynomial. Yeah. So what's going on in this expression here? Well, look at the numerator. Well, so this thing, remember, is a function of x. Yeah. So the numerator is just a bunch of products of linear terms. Yeah. In fact, the numerator is a polynomial, and the denominator is just a constant, right? It just depends on these input points, xi's. Yeah. So we're still good. This Lagrange basis is still a set of polynomials. This is not written in sort of our favorite basis, but that's okay. It's just going to change the way that we think about polynomials. Yeah. And why do we like the Lagrange basis so much? Well, it has a really funny property. So remember, what is our input again? Our input is a bunch of xy pairs, right? So I expect f of x1 to equal y1, f of x2 to equal y2, and so on. Well, look what happens if I plug in, for example, x1 into phi1. Yeah? Well, what is the numerator of phi1? Well, it's going to be x1 minus all the other data points just multiplied together. What's the denominator? Exactly the same thing. Yeah? So phi1 of x1 is equal to what? Leonard, what's it equal to? 1. Yeah. What's phi1 of x2? Well, notice, right? So the product on the top is the product over all j not equal to 1. In particular, there's a j equals 2 term in there. Yeah? So you're going to have x2 minus x2 somewhere hiding inside of that product, which means that phi1 of x2 is equal to what? 0. Yeah? So in fact, let's generalize this property just a little bit. We know that phi I of xl is equal to 1 when l is equal to I and 0 otherwise. We don't know anything else about the phi's. In fact, they can be pretty wild and crazy, but we do know that much. Right? Well, it's a ridiculously convenient property for interpolating using polynomials. Right? Because what am I going to do? Well, all I have to do is if I have a bunch of x, y pairs, right, then I just sum up y times the first guy, y1 times the first basis, plus y2 times the second basis, plus y3 times the third basis, and so on. Right? And then what happens? Well, let's actually just plug something in. Yeah? So this is gonna, So let's say that I have f of xi for one of these. Remember, we have all these xi, y pairs. I just grab one of the xi's and I stick it in there. Right? This is going to be the sum over all, I'm going to make this a j. Sorry. This is going to be the sum over all I of y, I, phi, I of x, j. You agree with me? But what is this number? Well, we know that he's 1 when I is equal to j and 0 otherwise. Right? In fact, we usually use notation called the Kronecker delta for this. Right? This number is 1 when I equals j and 0 otherwise. Just fun math fact of the day. Yeah? So in particular, only one term of the sum survives, right? And that's exactly the jth term of the sum. Right? So in fact, when I put f of xj, I get yj. Yeah? So this function is a polynomial, right? Because it's just a linear combination of these polynomial bases. And he satisfies the constraints that we want. Yeah? So I just took what used to be a problem of solving a humongous linear system of equations, and I turned it into just applying a formula. Right? By the way, do we know that the van der Waals system and this Lagrange basis will give you the same output? Any guesses? right? I mean, so I just came up with two different functions f of x, right? I can either write f of x equals this sum here, or I can like solve the van der Waals system and write this thing the monomial basis, right? Two different options. In fact, they give you the same function. And why is that? Well, let's take a look at the Lagrange basis. So let's say I have k data points. How many terms are going to be in this product in the numerator? That's the product over all j not equal to I. So I remove I. Yeah, so there's k minus 1 terms in the product. Right? If I have k input data points. Yeah. So what does this mean? This means that phi I is a degree k minus 1 polynomial. Right? Just like when we were talking about the monomial basis. Remember this guy downstairs here? He's a degree k minus 1 polynomial, because that's the highest power we see here. Right? Each of our basis functions is still degree k minus 1 in the Lagrange basis. Right? And our formula is just combining them. Yeah? So in fact, this form of f of x is some degree k minus 1 thing. Yeah? So, now what do we know? Well, we know that our Lagrange interpolation and that this van der Waals system give us two k minus 1 degree polynomials, and in fact there's a unique one of those that goes through k points. So you're done. Kind of a circular, kind of a weird argument, right? I never actually constructed the way to go from the Lagrange basis to the monomial basis, because it's kind of hairy. But in fact, just because you know that there's exactly one degree k minus 1 thing that goes through k points, so you're good. Cool? I know it's a lot of words. Yeah. Okay. Great. But, the question is, okay, so we really like this Lagrange basis, right? He's a basis for polynomials, and it makes the interpolation problem trivial. So, like, is our story done for the day when it comes to polynomial interpolation? And sadly, the answer is no. Right? Because of two different, in fact, there are two complaints that I have. So first of all, once I actually compute those coefficients A using the van der Waals system, it's very easy to find f of x for a given x, right? I just plug into that monomial. But how long does it take now? Well, now I got to do all these products, right? So in fact, I have to do order n things to find phi I of x. Right? There are order big O of n, or big O of k, I guess, terms in this product. Right? And in fact, outside of this product, I have a sum over k things. Yeah? So for each input x, how long does it take? Well, it takes k squared time for me to just evaluate f of x. Yeah? So I lost a little bit. In other words, my evaluation is slower, but the actual just writing the form of f is faster. That makes sense? And in fact, I have a second complaint, which is, let's say that I have a ton of these x values. Never mind what the polynomials are a little bit weird in that case. But in that case, I'm likely to have two x's that are very close together. Yeah? Presumably not equal, but they could be close together. And in fact, somehow you expect interpolation strategies to do well when you have x's that are close together, right? Because then you're interpolating, right? I've got a function like this, and it's like pretty clear what my function should do between those points, right? Because they're very close. But when x's are close together, what happens? Well, I'm multiplying a bunch of small numbers and putting them as a denominator, and as we've learned, that is a big no-no in numerical analysis, right? Because your IEEE floating point, whatever the heck, is likely to think, oh, he's just dividing by 0, and we're just going to give infinity or some very imprecise number back. Yeah? So we have these two different strategies, right? So we have this van der Waals system, which is slope, that gives a very numerically stable answer, and then we have the Lagrange basis, which is somehow faster, although still not completely faster, right? We went from n cubed to n squared, but there are some numerical issues. Yeah? And so one question is, can you compromise a little bit? And of course, this being a question in numerical analysis means that it has been studied to death for centuries, and in fact, continuing in our list of very famous mathematician names, the third very well-known basis is the Newton basis. And what does this basis do? Does everybody see? So this notation, I think, kind of hides that this basis is actually pretty simple. So for example, what is the first Newton basis function here? He's just psi. He's psi 1. By the way, I think the Heath textbook uses phi for any and all bases. I didn't love that, so you're going to have to be a little careful when you read. Right. So what is psi 1 of x? It's a product from j equals 1 to 0. Oh, sorry. So I defined psi 1 of x to be 1. So now let's ask what psi 2 of x is. Yeah. So he's the product from j equals 1 to 1 of x minus xj. Okay. So in fact, psi 2 of x is just x minus x1. Okay. By the way, do you guys see this is a polynomial? x1 is a fixed input constant. Yeah? Okay? And what is psi 3 of x? Well, he's just x minus x2 times x minus x1. Right? And so on. Yeah? Psi 4, I think, pretty easy guess, x minus x3, x minus x2, x minus x1. Yeah? Right, so this funky notation with all these products and stuff is a little bit tough to digest, but in fact it's usually encoding like pretty simple relationships. Okay. So the Newton basis, I claim, is kind of a compromise between the Vandermonde stability and the Lagrange speed. Okay. And how do we know that? Well, we can make kind of a funny observation, which is, let's say I put x1 into our basis functions, right? And in particular, remember, I'm going to write f as a linear combination of all these psi's. Yeah. Well, I put x1 in. What's going to happen? Well, if I go into psi 2, I have x1 minus x1, so this is 0. If I go into psi 3, I've got an x1 minus x1, so this is 0. So in fact, all the terms go away except the very first one. Yeah. Similarly, if I put in x2, then I notice that starting with this guy, I now have an x minus x2, and he appears in all the rest of the basis functions. Yeah? So you get, in the end, you get this sort of series of relationships, right? The f of x1 is equal to just the first term, f of x2, you get 2 terms in your sum, and so on. Right? And this is a structure that we know how to deal with in CS205A. Yeah? It looks triangular. Yeah? In fact, if I write down just these relationships in a matrix form, just like we did with the Vandermonde system, yeah, I get a lower triangular system of equations, right? Well, this is great, because what used to take us n squared time, or rather n cubed time, right, to solve that Vandermonde system, just using Gaussian elimination, right, we know that we can solve lower triangular stuff in n squared time. Yeah? So this is a much faster system of equations to solve. It gives you your c's, and it doesn't suffer from the numerical problems that the Lagrange basis has, because you don't have the denominator anymore. Yeah? So this is an interesting compromise. Right, and in fact, if you read in your book, I decided, and I think also in Ron's course notes, there's a specialized method you can use for solving this system of equations that also takes n squared time, but is like somehow more slick. It's kind of fun to read about, but this will take the same amount of time, so I'm not too worried about it. Cool. All right, so I'd say at this point we really have exhausted the problem of polynomial interpolation. Right? The idea is if I have k data points, I can get a degree k minus 1 polynomial that goes through those data points. Right? And we have 3 different bases that all accomplish the solution to the same problem. Right? Because there's a unique answer to that problem. Right? So since these are all polynomials and they all have the same degree, we know that accidentally we recovered the same thing, even though they're all in very different form. Yeah? That's a very important point. If I were looking for midterm or final exam,